Hey everybody, so in this video, I would like to do some analysis for you. I want to walk you through the analysis because I made some mistakes in the original lab write-up that I created for this. So I would like to talk you through the process to kind of help you out, okay? So hopefully you're following along this video at home as you're doing your analysis, okay? So we've actually worked up to the point, hopefully you were able to gather your data. In this Slinky lab, you were shaking the Slinky, you had different numbers of wavelengths, you were getting different numbers of loops. Each one of those represented a different wavelength for the wave going through your Slinky. And then you had to also measure the time that it took to go back and forth. Now, where we're at now is we're at this point where it's asking us to graph the data, all right? So in my spreadsheet here, this is what you likely have, the number of loops that were there, and then the wavelength, right? When I only had one loop from one side of the Slinky to the other, that was half of a wave. It just did the crest part of the wave. Or when it flipped upside down, it was just doing the trough of the wave. So that was half of a wave, okay? When I had two loops, my wavelength actually, it had a crest and it had a trough, and those were actually going back and forth, right? In this kind of standing wave. But that was representative of a full wave, right? Where it starts at the middle, it goes up, it goes down, and then it returns back to the center again. So that was a full wave. So you'll notice that my Slinky was 3 meters long. Your data will probably be different from this because I used a completely different kind of Slinky to what you guys use, just to show that different Slinkies give different results, but it should be similar. The idea, the analysis part should be similar to this. So I said based off of the number of loops that I had in that 3 meters, this is my wavelength. If you need help figuring that out, please come check with me, come ask me. We haven't done standing waves yet, but hopefully this will be helpful to you. And then I put my time here. I measured how long it took me to do 10 cycles. So I went 1, 2, 3, 4, 5, 10 times, right? And then I divided that by 10 to get this data right here. So this is actually what I'm interested in. How much time did it take for one cycle? Now I do this on purpose because you'll notice right here, the uncertainty between my data points, it goes all the way from 8.68 all the way up to 9.09. Okay, so that's about 0.4, so it's plus or minus about 0.2. So that's a normal uncertainty for using a stopwatch, is about 0.2 of a second. But when I divide that by 10, you'll notice that now the uncertainty is 0.02. And so therefore, my numbers are much closer together. I'm actually a little bit more precise. Those errors don't have such a big effect on my final results. And so that's why I've done it this way. And then I got the average. I added those three things together and divided by 3. And then I used that period to get the frequency. Remember, frequency is 1 over period. And so I was able to get the frequency in hertz. I've got all my units here. Everything's very clearly labeled, so it's easy to kind of follow along if you know what was happening in the lab. So what I'm going to do now is I'm going to copy my wavelength, and I'm going to copy my frequency. Okay, now I need to make sure that it only pastes the values. Okay, so I got frequency, I got wavelength. So now I'm going to highlight those two, and I'm going to say, insert for me a chart, please. And you'll see right here, it even put my units on there for me, wavelength in meters, frequency in hertz. Everything's spaced out kind of nice there. I'm going to go ahead and close this because I don't need it right now. And you'll see that I've got a very nice graph there. But you will also notice that my graph is not very linear. If you see something like this, please do not draw in a straight line and be like, look, it's close to all the points. That is not a straight line, y'all. That is a curve, all right? And most likely it is an inverse curve. Well, how do I know? Well, I know because we have a relationship for frequency and wavelength in waves. And that is that the velocity is equal to the frequency times the wavelength. And if velocity equals frequency times wavelength, then frequency and wavelength have an inverse relationship. Any wave in my Slinky will go the same speed every time. The wavelength and frequency will vary, but the speed of the wave depends on the conditions of the slinky, not on my wavelength and frequency. All right? So if I do this mathematically, here, come with me, let me show you. If I do this mathematically, what I'll see, if V is equal to wavelength times frequency, I do have frequency on the y-axis. If you'll look at my graph there, on the y-axis, I have frequency. So when we graph, we always want to try to linearize. Why? Because when we linearize, we have a slope, a constant slope, and that slope could mean something, right? We also have a y-intercept, and the y-intercept also very often means something. So I'm going to take this, I'm going to rearrange it so that I hopefully get y equals mx plus b. I want it to be a linear graph. So in order to do that, I need f to be all by itself. That's on the y-axis here. So f is going to be over there. Now sometimes it'll be the square root of f or f squared or sine of f or something like that. That's fine. But I need that f variable to be by itself. Okay? So I'm going to divide by lambda or multiply by 1 over lambda, however you want to think about that. But I'm going to move the lambda over to the other side. Now when I do that, I'm actually going to rewrite this so that the f is over on the left-hand side and the other stuff is on the right-hand side. So follow along with the math. So I'm dividing by lambda or multiplying by 1 over lambda. So I'm going to have f by itself, and then I will have the v times 1 over lambda, or v divided by lambda, however you did that mathematics. I've done it this way on purpose. The reason why I've done it this way is because I really want it to match up with y equals mx plus b. And you'll notice that on the x-axis of my graph is wavelength. And so wavelength being on the x-axis, I want that to be in the position of the x. So what you'll see now is that I have the y that is in the position of the frequency, and I have the x that has wavelength. And it's okay that it's 1 over wavelength because that tells me the relationship. That right there says that it is an inverse relationship. You'll also notice that there's nothing being added to the b. So I should have a plus 0 there. And you will also see that in the position of the slope, I have velocity. That means that if I graph this, if I put x as 1 over lambda, and if I put y as frequency, then my slope should be v. So that's what we're going to do right now. This is how we do this analysis. All right? So let me show you. I'm going to go back to my graph. I'm going to delete this one because this one is definitely inverse. And yes, you should include this in your lab, in your analysis, but I'm not turning in a lab, so I'm going to delete that just so that we have more space here. I'm going to redo this, but instead of these, I'm now going to take the wavelength, and I want the wavelength to be 1 over the wavelength. Okay? So I'm doing 1 divided by that. That's what we saw right here, is that I need 1 over the wavelength. And if I do 1 over the wavelength, then it should linearize my graph. So watch this. So I'm going to do that. I'm going to do 1 over 3. I'm going to do equals 1 over 2. I'm going to do equals 1 over 1.5. I'm going to do equals 1 over 1.2. Now, it is annoying to have all those decimals, so I'm actually just going to highlight that real quick. I'm going to go like this. That makes it look nicer, but the decimals are still there. If I want them back, I can just go blip, 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 and my decimals are back, just the way that they were before. So I'm just going to clean it up a little bit so it looks like this. So now I'm going to regraph, but this is no longer wavelength. This is now 1 over the wavelength, okay? Which is now not meters, it's now going to be meters to the -1 power, or 1 over meters will be my units, okay? That's okay. Now we're going to graph those. And you'll notice that when I graph those, I'm going to go Insert, Chart, okay? By the way, please notice that I am using a scatter plot here, okay, a scatter chart. If your graph gives you a straight line, if it tries to give you a line graph, tell it nuh-uh. If it tries to give you a bar graph, you tell it I ain't doing that. I am using a scatter. Anytime you're finding a relationship, you should be finding a scatter plot, not any of these other types of graphs. All right. So what hopefully you'll see now is that we actually have a fairly straight line. And you may say, but that doesn't have many of you are looking at this and saying, well, the y-intercept should be 0. The y-intercept isn't 0. Actually, the y-intercept is really, really close to 0. I don't know. I haven't actually done this data before. This is the first time I'm analyzing this data. But if I come in here, let's see, I can actually change on my horizontal axis. I can make my minimum value show up as 0. And what you'll see is that if I actually include the 0, 0 point here, that it's a pretty straight line and it almost goes through 0, 0. I could probably draw a line that gets close to all of those points and goes through 0, 0, right? In fact, that's how I'm going to finish off the lab, right? So if we're looking at this, I did do the graph of the data. That's where I got the nice inverse graph. And if you want to do it on the computer and print it out and cut it and paste it in here, that's fine. You can do it that way. Okay, the error bars should be included in there, right? I talked about the fact that I had about 0.02 error in my timing. My length is probably not quite that much. I'd maybe say 0.1 or something, but you could include error bars in your length as well. Okay, that would just be little bars that go off the side that show that that point could be a little bit bigger, a little bit smaller in either direction. That's fine. I described the relationship. Remember, I said it was an inverse relationship. I even went through the math of talking about it. And so therefore, we then went through this process, which isn't on your paper, but I've added it in here. So this now talks about the idea of trying to get it to match to the y equals mx plus b. Remember, when you're matching the y equals mx plus b, you want whatever's on the y-axis to be on the side by y, by itself, isolated. And then you want whatever's on the x-axis to be over on the other side so that it matches up with the m and the b. All right? So at this point, I've now graphed the linearized data. That's what I have here. This is a graph of the linearized data. It is pretty linearized. I'm actually going to go in there and I'm going to add in here in the customize. I'm going to go to series and I am going to add in a trend line. Okay, so for the trend line, yes, I do want linear. This is one of the things that I don't like about Sheets is it doesn't give me the option of forcing it to go through 0, 0. But I'll take what I can get. So actually, I don't want the r-squared value. You could get the r-squared value that tells you how good it is. But here I got the equation, 5.87 times x plus 0.0996, so 0.1. That's pretty close to 0. I think I did a fairly good job. If you do this on Logger Pro or if you do this on Excel, it'll actually allow you to force it to go through 0, 0, which is kind of actually what we want. If you're drawing it by hand, you should draw it through 0, 0 because we know from the mathematics that we should get a 0. As long as you can draw a line that mostly fits the points and goes through the error bars, then it's okay to force it to go through 0, 0. If going through 0, 0 causes you to go outside of the point significantly, or it causes you to go outside of the error bars, then in that situation, don't do it. Just fit the points with a straight line. In that case, there's probably some systematic error going on, and you want to figure out what's wrong. You don't want to deny the fact that something's wrong. You want to go through and figure out what is wrong with your data. All right? So with that, I've now graphed the linearized data now that it's linear. I drew my line of best fit. Please no zigzags, but if it is a curve, you can draw a nice smooth curve. But in this case, I just linearized it, so therefore it should be linear. All right, and then I'm going to use the graph to determine the speed. Now, when it says use the graph, what it really means is use the slope or the y-intercept. They really don't want you to just randomly choose a point on the line and put it into the equation, because that's not really using the line. That's using a data point. So they want you to go into the line. They want you to pick a couple of points, find the slope of the line. When you find the slope of the line, 5.87, what you'll find is that the slope, remember what we talked about here, in the y equals mx plus b. The slope was the velocity there. And so when I did mine, I actually got the slope right there, 5.87. So the speed of the wave for me is 5.87 meters per second. And that is the speed of the wave in the particular slinky that I had. Yours will likely be different. My guess is that most of you will have slower speeds because of the slinky that you had. That's fine. That's what you should expect. You should expect something a little less than 5.87 meters per second. Okay, so hopefully that was helpful. If you still have questions about what's going on here and what am I trying to accomplish and how do I do this data analysis, please feel free to come ask me or send me a chat or a question, and I'll try to help you out. Okay, but I'm hoping that this video was enough to support most of you in being able to do the analysis of the first part of this lab. Okay, that's it. We'll see you next time.